Alright, welcome to a bit of a weird lecture. I've got a bunch of just random topics that I'm required to teach to you, but I am not going to test you on them because they're just too small, I would say. So still pay attention, it's useful knowledge, but you can just sit back and relax. Alright, so let's talk first about something called register renaming, which is as it sounds. We're going to rename registers, but why? Alright, so I guess the goal when you're a CPU manufacturer is you want your CPU to be the very fastest, and so we're going to try and decrease the number of stalls as much as humanly possible. We're going to what? We're going to make a pipeline. We're going to add some extra execution units. We're going to make it a superscalar CPU. We're going to predict our branches and just make a guess, and usually our guess is correct. All of that is to decrease the number of stalls, okay? But in addition to that, the CPU is able to rename registers, surprisingly. Isn't that cool? So, it can do that if it wants to. It's got some extra spots, some secret registers that don't really have a name. And as long as everything is after the instruction is executed, as long as everything is in the right spot after all this is over with, it doesn't matter which registers it actually uses. Okay, so here's kind of what the CPU looks like sometimes. It's like, all right, this is register X0 usually, and this is like register X1, but sometimes it could be X3 instead. That's kind of weird to think about, I know. Like, okay, here's X5. Usually that's X5, but it could also be renamed sometimes. And then deep inside the CPU as well, there's like somebody else using X5. There's X5 number 2. Like, that's the kind of thing that the CPU is keeping track of. Like, what are the names of these places in memory that I'm calling these registers right now? Okay, it's crazy. But here's a better example probably. It's like, all right, the CPU sees this exact instruction, add X1 and X2 into X0. It's like, nope, you know what I'll do instead? I'm going to do X1 and X2. I'll add that into X5 because then I don't have like a read after write dependency, and I can like rename, or I can reorder instructions, and that will prevent stalls. All right, so that's perfect. All right, so that like maybe some other instruction that I'm running right now as well as using X0, and like I'm just gonna put the answer in X5 for a split second. Okay, so like the real X5 gets saved in like a secret X5 number 2 or something register. So that's the kind of thing that exists in your CPU. We have more than just 32 registers. The CPU gets to like pretend which one has name X0 right now and which one has X5 right now. Okay, so yeah, there might be 32 registers on the specification of the chip, but for the instruction set architecture, but there might actually be 80 registers secretly inside that can like at a moment's notice be called X0, which is wild, I know. So that's register renaming, but it's all about preventing stalls. Okay, so here's an example. This is of course higher level code, but pretend this is assembly. All right, maybe the CPU sees these instructions coming in, and it's like, uh-oh, I see some issues. Can you see the issues? It's like, okay, I'm going to read from memory, place into X1, and I'm messing with X1, and then I'm going to store the answer back in that, like a different place in memory. Okay, does that make sense? And then you do the same thing, right? You can see there's kind of like two different chunks. There's like using X1 to do this kind of memory stuff, and then using X1 to mess with this memory and change values and set the answer back. Okay, so this is like the original code. And this might be what the CPU translates that code into. It does the same thing, but it lets these two chunks of code be run at once. That's kind of cool, right? So they can be parallelized on your superscalar separate execution units. So can you see, like, all right, these X1s and these old X1s are kind of doing completely different things. So let's just call this X2 instead, and now this can be parallelized. Okay, so this is like what the CPU does. So now it doesn't have to worry. It can do both of these at once. Can be run at the same time. Isn't that cool? And that gives you better throughput, and your instructions are like running a little bit faster, and that makes you the top CPU manufacturer when you do this. So everybody does this now. Okay, so that's secretly going on. There might be 32 registers to us, but the chip itself might have like 80 or something. That it's just renaming all the time. Okay, so that's the first weird thing about CPUs. Look forward to that if you are a computer engineering major. So next thing is, let's talk about bus controllers and tri-state logic. So this is more like circuitry concepts that I, as a computer scientist, don't know too well, but I can still teach you a little bit. All right, so here's a picture, right, of what's going on in the CPU. It's talking to everybody, yeah. So you got a bunch of different kinds of buses, if you remember. There was a pretty picture. Here's another picture of that kind of idea. I guess I need to scroll in even more. Oh gosh, there it goes. So yeah, the CPU is the orchestrator of everybody. It's like when it talks to memory, it's like, okay, along the control bus, it's like, I would like to read to memory. So it sends read along the control bus, and then it tells along the address bus, like what address do I want to read from? And then the memory can hook this way, go back to the CPU along the data bus and be like, here's your address, here's the value at that address. And then this data bus is two-way, right? The data bus needs to be two-way because the CPU might try to write to memory. It's like, all right, I want to write to memory, so it sends the write signal along the control bus. It's like, here's the address I want to write to along the address bus. And then it sends the data that way, right, when it wants to write to memory. Does that make sense? So that's kind of what's going on there. And it can do the same thing with other things. Like, all right, you can also use addresses to talk to I/O. We know that. We do memory mapping now. So that's the kind of idea. That's what's going on in the CPU. The data bus, we say, is bidirectional. You can send information forwards and backwards because the CPU might want to send information to memory on a store instruction, and it might want to load from memory on a load instruction. Okay? Same with like the peripherals over here on your I/O ports. All that fun stuff is secretly going on. All right? So you can do reads and writes, and maybe I should draw those in different colors so that we can come back and study later. So like, okay, if the CPU wants to read from memory, if it wants to load, okay, it's got like a register it wants to place a value in. It's like it sends along the address bus, hey, go to this address, please. And then the memory gets ready. It's like, all right, I'm going to go to that address, and I will give you back along the data bus. It also sends a read signal. I'll give you back along the data bus my value, and it stores it in its little register. Okay, so that's like a load. A store would be the opposite. It's like, all right, I want to write to this memory address, which is above that one, I guess, AB. And, okay, I have a value here in this register. Take that. I'm going to send write to memory. I'm going to shove that to you along the data bus, boop, and it's going to go into memory where it needs to go. That's kind of the goal. Okay? I hope that makes sense. That's what's happening there. And then the same thing is true about like the I/O ports. You can send information along the data bus, and like you can get values back onto the CPU, like what key was pressed, or you can send values. So there's also little registers there that you can like access and talk to. So, okay, let's zoom back out now. So this is a bidirectional thing. It's one wire though, right? It's one wire where you could either send information that way or you could send information that way. It's really like a bunch of wires at once, but you get the idea. Okay, you send bits at a time. It would be a problem, right? It would be a problem if somebody tried to send along the wire and somebody tried to receive along the wire. Okay? Let me try and explain to you why. It has to do with electricity. All right, if two peripherals, for example, or like the CPU wanted to do a read at the same time the memory was like dealing with a write, like there were two things being passed along the data bus at once in each direction, that would like involve somebody sending a 1, right, and a 0 at the same time, potentially. If two peripherals, one wanted to send a 1 and one wanted to send a 0, for example, what's going to happen? It's like you got two I/O ports. Let's say that that's what's happening right now. This is the keyboard, this is the mouse. They're both trying to send information to the CPU, for example, along the data bus. You could also imagine that like they're talking in two ways. If somebody wanted to send a 1, somebody wanted to send a 0 to the CPU, what is a 1? It's high voltage, right? What is a 0? It's low voltage. Source in a sink, kind of. It's like electricity. And which way does electricity want to travel? It wants to travel from like the 1s to the 0s, from positive to negative, right? All the way to ground. So what's going to happen if two people try to use that data bus at once and try to send opposite bits along whatever wire we're talking about right now? This will happen. The information will not get to the CPU. The electricity will flow that way, right? And that will probably blow up the peripherals. That's a bit of a problem, right? That's a bad thing, okay? It's like if you hooked up a battery. Maybe you did this when you were a kid like I did. You hook up a paper clip to the battery, right? You unwind it, and like one side's going to the positive terminal, one side's on the negative terminal. This heats up the wire, yes, because it's just it's like a short circuit, and like it's all stuff is traveling that way. So like from a 1 to the 0, yeah, that's a problem. We don't like that. That burns things, and that will definitely fry your processor or the peripherals involved, okay? So you don't want two people talking along the data bus at once. That's the moral of the story. So in order to keep this kind of idea from happening, we let what's called the bus controller manage, right? It's the driver, and it's telling the devices, like, whose turn is it to use the data bus right now? That's the idea, okay? So yeah, there's a bus controller that's managing, like, okay, only one of you can use the data bus right now in one direction. It makes sure that everybody else is cut off. And one way to cut people off is to use a tri-state buffer, all right? So yeah, the bus controller is going to use like a tri-state buffer, usually, to switch circuits, not like 1s and 0s, but like completely open, completely closed. You don't get to talk to anybody right now, all right? So a tri-state buffer looks like this. Here's a cute little example of like what's going to happen. This is like everybody's sharing this bus, and then you got some tri-state buffers along the way that enable you to use it. Like somebody's telling you that you can use it right now. So here's what a tri-state buffer looks like. Okay, you can send enable on the enable line, and it lets in be connected to out. All right, so if something is enabled, there's a 1 coming along here, it lets in go to out. It's like a wire at that point. All right, or if you send a 0, dun, 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 it kind of opens the circuit. That's the idea, okay? There's that. And so yeah, there's actually a secret third thing, okay? So the tri-state buffer uses tri-state logic. The output values that you could see, depending on this enable line, it might need like 2 different bits to talk about 3 different ideas. The output values, right, you can connect in this way. There's like three options for you. You could say the enable is 0, right? And that means in is not connected to out at all right now. It's like an open circuit, if that makes sense. That's called high impedance, an open circuit right now if you're not enabling anything to travel. It's like no information can go this way, no electricity can flow, all right? And that's perfect for our cases. That's making sure that no 2 people can use it once. Somebody's cut off, okay? That's what's going on with the tri-state buffer. And then if the enable is a 1, let's use green for that. If the enable is a 1, then in is connected out, and you could send either a 0 or a 1, of course, along this. And then it's like it's connected, and you could send whatever you'd like. So there's kind of 3 options coming out of out. You could see a 0, you could see a 1, or you could see no electricity flowing at all. We call that high impedance, okay? And that makes sure people get cut off, and your circuit won't get shorted, and nothing blows up today. All right, so that's what a tri-state buffer is all about. And it's the job of the bus controller, which is in the CPU somewhere, telling everybody who gets to do what. They're setting these enable bits along each wire that is the data bus, okay? So yeah, I hope that makes sense. So everybody has one of these, and that's the idea, all right? I think the last thing that I want to talk about today, it'll take some time though, is other assembly languages, because why not? You've learned one, you should learn the rest. So let's first talk about the closest cousin to what we've been talking about so far. Let's talk about 32-bit ARM assembly. All right, 32-bit ARM assembly. Here's what it looks like. Okay, you have, first of all, not as many registers. You got 16 registers, and their names are different. So whenever I messed up and I said R something, this is why, because I used to teach 32-bit ARM assembly in this class instead of 64-bit. Here, what your registers are called. You get R0 through R12, and then you also have R13, 14, and 15, but those have special names. Those are your SP, LR, and PC. In Rs, we have, I guess LR does have it has a number associated with it, but SP is completely separate. It doesn't have like a normal number in our 64-bit ARM CPUs. They changed that idea. And then also, you were able to talk about PC itself. You could get the address of your current instruction. That was a register you could access in 32-bit ARM assembly, but we don't get access to that anymore in 64-bit ARM assembly. I guess they decided that was a bad idea. But yeah, that's what's going on there. And each of these registers, of course, in a 32-bit assembly language means the CPU only has registers that are 32 bits wide. All right, so 16 registers, they can hold 32-bit values. Okay, if you want to hold 64 bits at once, you can't do it in a single register, which is wild because that's what we're used to right now. But what could you do? You could combine two 32-bit registers. You can be like, all right, I'm going to put the high bits of a 64-bit number in R0 and the low bits in R1. That would work. That's kind of as good as it gets for you. Okay. There is no 0 register because you only got 16 registers total. Like, that would be a waste. So you just gotta move 0 with the move instruction if you need the number 0. So there's that, and honestly everything else is pretty much the same. You still have like scratch registers versus saved registers. There's more in 64-bit ARM assembly, but you still get the idea, right? One cool thing that you could do in 32-bit ARM assembly is you can mess with PC, because like you can talk to it, you can change PC. Like, our ret instruction is essentially this if we could do it. You could do this in ARM32. Isn't that amazing? Just like move LR into PC, like that will jump for you. That's kind of cool to think about. All right, so let's see, what do I want to do? Let me just show you like what a squaring function looks like. It's very, very similar. Like, your arguments again are going to go, your first 4 at least are going to go in here, and then you have to start using the stack and all that. But yeah, let's go to godbolt.org, and I'll set it for 32-bit ARM assembly instead of 64-bit. Whee! So I guess let's keep it that big. But ARM 64, is there ARM 32? ARM, oh gosh. They might have got rid of it. It could be this one. I don't know. Let's look at it. ARM v8. No, that's still 64-bit. Let's keep scrolling then. LLVM. If there's MIPS, there should definitely be. RISC-V is a cool new kind of processor. I really don't see it. They might have got rid of it. That's way too bad. I swear it was here a year ago. But they might not have it anymore. There's 64-bit ARM. Okay, there's just normal ARM. There we go. Cool, we found it. That's what I'm talking about. So let's make this bigger. So let's make it like a square function. And int num. What do you do in a square function? You return num times num. All right, what's going on? How does this look? To mess with the stack, like there's nice push and pop instructions in ARM32, so that's much better than it used to be, sadly. Or sorry, it used to be much better. Now we're stuck to, we have to like sub SP and like do a load. It's too bad. But you used to just be able to push scratch or like saved registers and pop them later. So there's that. What else do I want here? So this is kind of a silly amount of things to do. Let me just show it to you. Yeah, so like squaring a number is just like, all right, the parameter is an R0 this time. It's an int, and so it's taking up the full 32-bit register. Just multiply it into itself, and this is how you return to LR. This is like their ret instructions, like branch to the contents of this register. That's what it's doing here. This unoptimized thing is like doing weird stuff with the stack for no good reason. It's like storing the making room on the stack for more than just this. It's using this saved register to store your argument for no good reason, storing it and loading it right back, multiplying, moving the answer into the return register, R0, just like X0 is where you return to. So that's happening. It is, let's see, for no good reason it's doing that. It is there. Okay, that is why it's doing that. So it's restoring the stack to where it used to be and getting the values back in the saved register even though it didn't need to use it. So yeah, it's all understandable, right? It's really not too hard. This pushes a register onto the stack and changes SP at once. So that's the only kind of new thing. And this is like the ret instruction, return to whatever's in LR. That is kind of the idea. So yeah, I hope that makes a little bit of sense at least. That's 32-bit ARM assembly. All right, let's do fancier ones. So this is Intel assembly. So Intel is x86, 32-bit x86. So we're talking about Intel processors, or anybody who uses that instruction set architecture, like AMD processors as well, are using this kind of thing. So back in the day, there was 32-bit Intel assembly. There are weird things about it. All right, so here's, you only get 8 registers, so it's 32 bits, so you only get 32-bit size registers. You only get 8 of them. They're called EAX, EBX, ECX, all these, they got weird names. You do have a stack pointer, like everybody needs that. And you get, you can access the PC, that's EIP for instruction pointer. You can't write to it though, okay? So you only get 8 registers, so you're kind of stuck. Like you don't have enough to do what you need to do usually, and so you're forced to like use the stack a whole lot more in Intel processors in 32-bit land. So there's that, and then also the instructions look a little weird because you only have like 1 operand per instruction. So instead of like imagine you had an instruction, then you're trying to like compile this idea of like x equals y plus z. Instead of that, it's going to be translated into, you can't really do like an add instruction. Add these 2 registers into this one. In Intel assembly, it's more like, it's a plus equals, like add into x, this 1 value. Add into x, this 1 value. So like, this will turn into, like in ARM, you could have made this 1 instruction. In Intel, this would have to be 2 separate instructions, right? So there's a couple different kinds of Intel assembly. This is like the default way that GCC uses, so that's why I'm showing this to you now. I think that's what your book shows as well. But everything's a little bit backwards. So like here's an add instruction, for example. It only takes 1 thing. It's like takes the thing you want to add into EAX. Okay, so it's backwards. All these instructions are backwards, and also you have to use percent signs and dollar signs for your constants instead of number signs. Weird. So yeah, this is kind of like, here's how to read both of these instructions. This is a move instruction that is kind of doing the equivalent of a store, because it's taking a memory address, it's computing a memory address. Like here's an address in this register, go 8 bytes later, so like it's adding 8 to EBP. So like this is kind of like this ARM equivalent, EBP plus 8. That's kind of what that means. And like take whatever's there in memory and put it into, sorry, it's a load instruction, not a store, and it's placing it into a register. Okay, it's backwards first of all, and yeah, it's going to memory, calculating this address, and placing the answer in that register. With a move instruction, there's no like separate load and store, and then add is doing this. It's like taking a value and adding it into whatever's already in the EAX register. Okay, so that's a little bit different. There's here's an example in your book. We can go through 8.5.2, I guess. Feel free to read this chapter on 32-bit x86 and 64-bit. Which one? 5. It's an example of a function. Okay. So I'll try to walk you through, like, here is some code. It's doing some silly stuff. And we'll try to look at what it was translated into. It's doing some stuff that's like undefined, first of all. Like this function, just setting a variable, returning its value. This function is making a variable setting to nothing, like it's undefined, and then returning it +2. So it's doing weird things, and this is what it's running for some reason. All right, so here's the example that your book wants to show you, and let's try to talk through at least one of these examples. So like this assign function, what's it going to do? All it's trying to do is make a variable holding 40 and return that thing. So what does that look like in assembly land? So this is 32-bit x86 Intel assembly. So okay, what's it going to do? It's usually going to like set up this register. EBP stands for base pointer. This exists also in ARM, but we don't really use it in this class. It like sets like where you want, like where is the top of the stack right now, and then I will reference that as I put more things on the stack. Okay, it's like these 2 lines, more or less, exist always in every like Intel assembly thing. It's like always using EBP and like moving ESP into EBP right now. It's like I would like to mess with EBPs like a saved register, so I'll save it on the stack. I'll push it, and then wherever ESP, wherever the top of my stack is right now, I'm going to put it on EBP, so I'll use that later. I'll be like my reference, my window into the stack. Because pushing messes with ESP, so like I'm going to save where the top of the stack is right now in EBP. And you could do that too in ARM assembly. Like this is very common. And then now it's messing with ESP, is like making room on the stack. And that's going to be enough room at least to hold an integer. It's more than it needed, but it's going to do that. So it made 16 bytes of memory because it's 10 in hex, subtracted from the stack, and it's going to put the number 40 in the stack. That's where it's going to save this value. So 28 in hex is apparently 40, and it's going to shove it using EBP. So I just subtracted from the stack, right? I've got room in the negative parts, right? Because EBP was the old stack value. I've just subtracted, like, go earlier in the stack and store a value there. So it's using a negative offset, which is interesting to think about. So it's moving this value into this place in memory, all right? So it's a little bit backwards to what we know. And then it's going to return that value as well. So it's going to go and get it out into the return place. It's EAX is the return register for return values. So like go into that place in the stack where we just made that memory and shove it into EAX. This leave instruction is kind of the counterpart to this. Just like this is always the header for every function. This is always the epilogue for every function. It's like leave just means restore EBP, get everything back to how it was, restore the stack back to how it was, and then ret just like goes back to the return address which has been placed on the stack for you. All right. So yeah, these are variable length instructions. So ARM, first of all, 32-bit ARM, just like 64-bit ARM assembly, every instruction is 32 bits wide. For x86, it's a CISC, right? Complex instruction set computing. So like this push EBP instruction, that's only 1 byte. 2 bytes for this move. 3 bytes for this sub. It's like it's a variable length instruction. Like this one is like this move has the potential of like in the immediate part encoding an entire 32-bit value if you wanted it. That's crazy. Stored in little endian. But like, yeah, hopefully you can kind of see the ideas. And it's like, here's some other functions that are going to do similar things to messing with the stack, to call functions. Your arguments go in special places. This assign function didn't need anything. I think that was a void. Okay, neither of them needed anything, sadly, but the printf, for example. Printf needs some arguments, and those arguments are going in where? So it's a call instruction to make a function call the address where the function lives. And then it's, where is the arguments? Where are they going? Are they going on the stack? Okay, yeah, maybe this architecture, it's been a while. I think 64-bit for sure uses registers for arguments, but I think it's the stack where you put the arguments in 32-bit assembly. Everything goes on the stack. Because, yeah, it's messing with the stack right here. Yeah, that has to be it. And then, yeah, leave and ret, like EAX is getting 0, so returning 0 from main. Okay? So, yeah, please read this entire chapter if you're interested in this kind of thing. Honestly, probably chapter 7 is more interesting to you, because if you have an Intel processor in your computer, it's 64-bit these days. But like this is going to help you understand the 64-bit one. All right? And surprisingly, of course, this is an Intel processor, Intel assembly, but 64-bit Intel is what I want to talk about next. But it's called AMD 64 because I think they were the first ones to bring the Intel. Okay, so they're like the first people to bring this specification onto the market, and so it got called after their name, even though they're a different company. So 64-bit Intel assembly looks like this. You've got 16 registers that hold 64-bit values this time, which is nice. Double what we had in x86. Still not as many as we have in ARM land. This is crazy. They still have to use the stack more than we do. So here are your registers. You got REX, RBX. Honestly, most of these registers got their E's changed to R's. They still exist, all right? And that's the thing. It's just like the X and W registers. So those all exist. Those are the old ones. And then there's some new registers, R8 through R15, because they ran out of letters, I guess. And all of these R registers they hold just like the X registers and the W registers, like the equivalent to an X register is the equivalent to like a W register. It's like X0 and W0. RAX means the whole 64-bit thing. EAX means just the lower 32 bits. And you can also get at the 16-bit thing. Like originally, Intel processors were 16-bit processors. And so you had the AX register, the BX register. And you get the upper half of that and the lower half of that. You can get individual bytes in your registers. The upper half of the 16 bits of AX, the lower half is like the lowest byte in this register, AL. That's kind of cool to think about. PC is called RIP, which is funny, and just like it's the corresponding thing of EIP, right? Just longer, 64 bits now. And yeah, you can still access those pieces of registers. You have finer granularity, you have more control because you can get at 16 bits and individual bytes as well. We just had W registers, that's as small as it got in RS 64-bit ARM. Yeah, pretty much everything else is 32-bit x86 similar. It's all the same. Let's go through the same example in Chapter 7. So I think they have this exact same code in Chapter 7. Boop. So legitimately the exact same code right here with the weird undefined behavior still. What's it doing? Let's go through assign again. So this was like make a variable, return the value. So okay, it's again gonna save the base pointer so it can do stuff with the stack. Mess with the stack, please. So that's what it's doing. The top of the stack is now in RBP because you read it backwards, and now it's moving. It's made space. I guess, yeah, it's not even subtracting from ESP or anything, or RSP or anything. It's just like, okay, yeah, above that, with a negative offset, I'm going to store the number 40 there, and I'm going to also put it in EX, because I still want to return a 32-bit int, right? So EAX is still where that goes, it's not RAX. And then it's going to pop that saved RBP value and return. It didn't even need to mess with the stack because it was like optimized. Didn't have to subtract from the stack. It just like, all right, I'm going to use a negative offset. That's fine. It knew that wasn't being used. So that's kind of funny to think about. And now it's retq because it's returned to a 64-bit value on the stack, 64-bit address. So Q for quad, I guess, right? And then back in main, the way that you call functions again, it's call Q, right? So they wanted the ability to call 32-bit things as well as 64-bit things, I guess. It's all very backwards compatible. So it's call Q for all of your 64-bit function calls. And then here's the printf call, and it's setting up the arguments in this way. It looks like it's ESI and EDI for your first two arguments. I believe that's true. So you got one argument is the format string, and then the next one is like the value you want to print because it has it looks like it has an int that it wants to print because it's getting that back from the adder function call. So, all right, how's it going to get all that? So, apparently this is the address of the string, I think. It's like, no, I think EDI. Yeah, it's EDI then ESI, so it's kind of doing it backwards. EDI is the first argument, so that's apparently the address of the string, format string. And then ESI is going to be... ESI is going to hold the integer that it just got out of the stack because that's where it saved that variable's value. That's the second parameter to printf. And then EX, changing EX here is not very necessary, I don't think. It shouldn't be necessary. Why it's 0, I'm not sure because it's going to do it right after as well. So that may just be some unoptimized thing or something that I'm not familiar with. But yeah, the call to printf, like this was the first argument, EDI. ESI was the second argument, and there were only two things. So that should do it. So yeah, hopefully that makes sense. Feel free to read the rest of this. Like it has some diagrams for what's going on for all of these bad boys. And it's going to draw what the stack looks like and how the undefined behavior is happening. It's very useful. But I think that's all I wanted to say here. So you can kind of see how the calls are getting worked on. Like how we're getting back in main. So I highly encourage you to read through this. Maybe we can look at like where are those arguments? What's happening here? Why does it do that for EAX? Zeroing it out. Does it say? resets EAX with the value 0. Nope. There is no need because we're going to do it again anyway. That's pretty funny. And then we're back here. Clean up the stack, prepare. Yeah. Make sure that 0 is the return register's value because we're returning an int. So yeah, I have no idea why we're putting 0 in EX before the printf call, because the first 2 arguments were in other registers. So yeah, I guess that's that. So yeah, good example. Hopefully that makes a little bit of sense, but those are some competing assembly languages for competing processors. This is the other big one. This is the one that ARM is competing against right now. 64-bit Intel is in pretty much every Windows machine. So yeah, hopefully you agree that that was not really horrible. Okay, they're all von Neumann architectures, every one of these. And honestly, the second you learn one, it's like, all right, there's not too big of a difference between them. There's just different names maybe for the instructions, but they're all going to do the same thing. They're all going to work in the same way. They got registers, they load and store from memory. That's pretty much it. So yeah, that's pretty cool. Pretty cool to know that you can learn anything right now. Go and learn your favorite assembly language, because it's going to be very similar to what you know now. So yeah, that's a couple things that I'm required to teach you, or were fun to talk about, but I will not be testing you on. So yeah, hopefully that was fun knowledge to learn, and that is all I have to record right now. So I will see you in the next video.